Hi there, Tanya. I have decided to do a video answer for your question because it involves graphics with charges, and you'll be better understand uh, how to work out this problem using video. And because I can't do that on the platform that we have for answers, I decided to make this video and use the whiteboard to express the answer. Okay. So this is an electric charge problem. You got three charges. You got charge Q1, which is a negative charge of minus 4.6 times 10 to the minus 6 coulomb, as you can see here on the board that I already put the charge there. You got Q3 right under it. It's a positive charge of plus 8.3 times 10 to the minus 5 coulomb. And then you got Q2, which is to the left, and that's also a positive charge of plus 3.75 times 10 to the minus 6 coulomb. You also have the distances between the charges. Between Q1 and Q3, you got 0.2 meter. Between Q3 and Q2, you got 0.2 meters. And between Q2 and Q1, you got 0.283 meters. You're also given that this angle here is 45 degrees at Q2. Okay. So let me ask you a question. If this is a 45-degree angle and this is a 90-degree angle, then should this be 45? Yes. So it should be a 45-degree angle. Because what? The sum of all angles in the triangle should be 180 degrees. So now we know that this is a right angle triangle with two equal angles, 45 degrees, and a right angle of 90 degrees. Okay? And we can verify that the hypotenuse is 0.283 meter by taking what? The hypotenuse of that is equal to what? Equal to square root of this distance is squared, so 0.2 squared plus 0.2 squared. If you do this calculation, you're going to get the hypotenuse at 0.283 meter. And what are we doing here is we are verifying the geometry that we have here. You're given at that distance between Q2 and Q1 to be 0.283 meter. I just verified it here. And why I verify this here, that this is the same. Therefore, we're also verifying the geometry of the charges in the figure. Okay, which is very important, and because you will find out why is it so important graphically. But anyway, before we start this problem, we have to understand what are the direction of the forces that are acting here between the charges. Okay, and we know that like charges, which is a positive, they repel each other, and like charges of negative, also repel each other. But unlike charges with positive, attract each other. So let's just see between Q2 and Q3. That's a positive charge at Q2, plus 0.75, and a positive charge at Q3 also. Therefore, the forces will repel each other. So if we are to graphically represent these forces, I'm going to draw that in a different color. Let's draw it in red. The forces will be like so. They are repelling each other. Okay, like so. What are we interested in? We're interested in finding what is the net force or resultant force on Q2. Well, first of all, let's see what are the forces acting on Q2. Well, the forces that are acting on Q2 is this force, which is pushing on the charge Q2, this force here, okay? And I call that force F heading from 3 to 2. I call that force F32. Okay, F32. And what are other forces acting on this Q2 charge? Well, we have, this is a positive charge, Q2, and a negative charge, Q1. Therefore, these forces, these charges attract each other, like so. So I'll draw the forces. And the arrows, they attract each other as if they want to collide with each other. So the direction of the arrows are going to be like so. Okay? So now if we take this force Q2 alone, we take, I'm sorry, this charge Q2 alone, I'm going to draw it here separate. This is my charge Q2. It has a force. I take a free body diagram, which basically, if I cut this section through here, like that, I'll take a free body diagram. I have a force, which is this force here. Okay. Pushing on it, and the force pulling away from it, like this. Okay. Now this, we need to find this force, which is F32, because this is charge Q2. Okay. The force is pushing from 3 to 2, and the force that's pulling away is force 2, 1. Okay, which is a pulling away force from charge 2 to charge 1. We know that this is 45 degrees. So we need to find the resultant force that is being applied on this charge. Okay, so first of all, we have to find the forces. So the forces are found by the Coulomb law, which simply state that the forces between electrical charges is equal to a constant K times Q1, Q2 over R squared. Now, the Q1 and the Q2 are arbitrary charges. We have to change the numbers as we basically work with this problem. So if we want to find the force of 3,2, now the constant K is a constant charge, and that's equal to 8.988 times 10 to the power 9 Newton meter squared per Coulomb squared. Okay, you've seen this before, I believe, but that's what this is. So I'm not going to keep putting it here. I'm just going to write K here, that value, times. What's Q1 and Q2 in this case? Well, for force 3,2 will be Q3, Q2, right? Divided by what? R squared, which R in this case, which is R32, equal to K times. What's Q3? Q3 is plus bear with me here a second, 8.3 times 10 to the minus 5 coulomb times Q2 is what? 3.75 times 10 times 10 to the minus 6 coulomb divided by R32 is 0.2 meter, and that's, sorry, R squared, okay? R32 is 0.2 meter squared, 0.2 meter squared. And the value of K, we know what it is. Notice here what's happening. You got coulomb times coulomb gives you coulomb square. And so this cancels out with here, K. And then you've got meter squared, cancels out meter squared, you're left with Newton, okay? So if you compute this and you put the value of K of 8.988 times 10 to the power 9 Newton meter squared per coulomb squared, if you compute this, you get 69.95 Newton. So that F32 force is equal to 69 69.95 Newton. So how about F21? Well, F21, which is this force, is going to be K, which is the same, times Q2 times Q1, Q2 times Q1, over R between 2 and 1. So R 2, 1 squared. Excuse the graphics here a little bit. So K, we know what the value is. We just put it in. So what's Q1? What's Q2 and Q1? Well, Q2, notice, Q2 is a positive charge, plus 3.75 times 10 to the minus 6 coulomb. So plus 3.75 times 10 to the minus 6 coulomb. Okay. And what is Q1? Q1 is minus, it's a negative charge, so I have to put that in its value, negative, minus 4.6 times 10 to the minus 6 coulomb. And that's divided by what? This distance, which is 0.283 meters squared. Same thing. We've already talked about how the units cancel each other's. If you compute this, you're going to get minus 1.94 Newton. Okay. So now we have assumed that the force that's acting is acting positive in this direction, right? But the value of the force came up to be negative, which means that the force is going to be heading the direction of the force. Now, this force was assumed positive pushing on the Q2, and the value came to be positive. As you can see here. Okay. And this force was assumed to be pulling away from Q2 and came out to be negative. Therefore, the force direction is actually in the opposite direction, which means the force is in this direction. Let me draw that force in a different color so you can see it. Let me draw it in magenta. So the force is actually like that. Okay, which is F21. Okay, so now on the next second board, I'm gonna simplify this more. You have this charge here. No, little circle. That's a charge. You got a force that's heading in this direction. I'm gonna make it big because it ended up to be a large force, which ended up to be what, 69.9 Newton. And you got a little force like this of 1.94 Newton. Okay. Actually, I'm gonna draw this outside. I'll write this outside because I'm gonna use that space for something else. So 1 point, no. 1.94 Newton. And that's your charge Q2. Okay. So how do we find the resultant? Well, we can join these head to tail. 1, 2, then the resultant force is going to be like this. And let me draw this resultant force by different color. I'll draw this force by green color just to illustrate better. So this resultant force here is a resultant force R, and it's equal to, we do not know. Okay, we do not know what that, we're going to have to find that out. Well, all we know, if I extend this a little bit like this, I know that this here is 45 degrees. Agree? And so if this is 45 and this is 180, how much is this angle? This angle will be what? 180 minus 45? 135 degrees. So this angle here will be, let me draw it in a different color. This angle here is going to be 135 degrees. That's all I know. But I know the values of these forces. So how do I find R? Well, the resultant, R, is going to equal to, by the cosine law, square root of this leg squared, which is 69.9 squared, plus this leg squared, which is 1.94 squared. $69.95. Sorry, 0.95 squared. if you compute this, you are going to get, oh, wait a minute. Okay. Now, what's the law of cosine says? The law of cosine says that this squared, this leg squared plus this leg squared minus 2 times this multiplication of the legs, which is 1.94 times 69.95 cosine what angle? This angle here, the angle that is opposite to the resultant. So that's cosine 135. Okay, so R is going to be, I have to compute this because I have not completed this problem before I started it. 69.95 squared plus 1.94 squared minus 2 times 1.94 times 69.95 times cosine 135. That is square root of 5088.6. So the resultant is square root of that 71.3 Newton. So this value now we found out to be 71.3 Newton. So we know the value, but we need to know the direction. Well, the direction is measured from where? If you are to draw this like that, the x-axis, the direction is going to be this angle theta here. That angle, let me draw this better. It's going to be this angle theta, measured from the positive x-axis, counterclockwise positive. So if we are going counterclockwise, it's positive, and clockwise negative. That's the sign convention of rotation. Okay, so how do we find this? Well, we know that this angle here, from here to here, is 180 degrees. So the whole angle theta is going to be what? 180 plus what? Plus this little angle here, I call this little angle alpha. Okay? So how do I find alpha? Well, I have this angle here, 135. I have R. I have this force. I need to find this angle alpha. This angle alpha is found by the sine law, which basically says that sine of the force of the one leg divided by sine of its opposite angle is equal to the force of the other leg divided by sine of its opposite angles. Therefore, we can write this as R over sine 135 is equal to 1.94 over sine alpha. So R, we have one, we know what R is. We want to find sine alpha. So sine alpha, if we arrange this, we get sine alpha equal to 1.94 over R sine 135. Okay. So 1.94 what's R? R 71.3 times sine 135. So if I do this calculation, I get sine alpha. I have to calculate it. So it will be 1.94 divided by 71.3 times sine 135. I got 0.0192 24. 1.92. I got 0.01924. Therefore, how do I find alpha? Well, I take the inverse sine of both sides. So I get sine inverse of sine alpha equal to sine inverse of 0.01924. Okay, so sine inverse of sine alpha implies that sine inverse sine alpha is alpha. Sine inverse of sine alpha is alpha equal. So I'll just take sine inverse of this value. Second half sine inverse of 0.01924. I get 1.1 degrees. 1.1 degrees. Okay. So what did we say? That the angle that defines the position of the vector r, which is a force vector r, is, well, it is 180 degrees plus that alpha. So it will be 180 plus 1.1 degrees. It's equal to 181.1 degree positive, rotating counterclockwise from the positive x-axis. And that is your direction of the resultant force R. I hope this satisfies your query, and if you like what you saw, you can always contact me and set up a lesson through Wyzant. Take care.